everyone, welcome to part 3 of chapter 4. Last time we learned all about how to do conversions. We talked about the metric system and how those powers of 10, right, those prefixes allow us to easily convert between units that are bigger or smaller than our base unit. And we learned how to do all of those conversions using dimensional analysis, which I told you I typically call train tracks. That's going to be a really handy problem-solving tool throughout the entire course this semester. And if you go on in chemistry, you'll use it there as well. It's kind of a foundational chemistry skill that you're learning. Today, though, we're going to learn how to do 2 different types of conversions that don't require the use of those, that dimensional analysis or the train tracks. Today, we're going to learn how to do temperature conversions, and also we're going to learn how to do calculations using density. So let's go ahead and get going. So first step, we're going to talk about temperature. So whenever we talk about temperature, we need to really talk about thermal energy. And thermal energy is this form of energy involving the motion of small particles of matter. And we will usually measure this by using temperature. Okay, temperature, we normally think of as being, hot or cold, or, the weatherman will tell us it's 72 degrees outside, right? But that temperature is actually a measure of the intensity of the thermal energy of a system. Okay, so it's actually talking about, when we're talking about temperature, we're actually talking about the motion of small particles of matter, which is kind of interesting. So the faster those particles of matter are moving, the higher the temperature. And the slower those particles are moving, the lower the temperature. So we can directly tell how fast these particles are moving based on the temperature, which is kind of cool. So whenever we talk about thermal energy and temperature, we also have to talk about heat, okay? And you're likely familiar with that already. I want to talk about the chemistry definition of it, though. The chemistry definition talks about the flow of energy due to a temperature difference. So when you think about something being hot or cold, right, that's a measure of how much thermal energy that substance has. So something that's hot has a lot of thermal energy, and something that's cold has less thermal energy. When you put something hot next to something cold, right, that hot thing actually will transfer energy to the cold thing and kind of warm it up. So, let's think about, if we have something that's hot and something that's cold, the heat will flow from the hot thing to the cold thing and, like I said, warm it up. The heat is always going to flow from higher to lower temperature, not the other way around. If something is cold, it just means it has less energy, right? And something that's hot has more energy. So when we talk about heat, this energy that's moving, that's called heat. So you can't have heat, if that makes sense. You can have a lot of energy or you can have less energy, but the flow of energy between two things, that's what we're calling heat. So heat is energy that is moving. Okay? So the SI unit of temperature is called Kelvin. Okay, you are likely familiar with measuring temperature in Fahrenheit, right? That's what we use in the United States. We're actually one of very, very few countries that uses Fahrenheit. Most countries use Celsius, and that's actually what we'll use most of the time in chemistry. Remember, chemistry is an international language, so we use temperatures that most of the rest of the world uses. In addition, they actually work out better in our calculations, so that's another reason that we use it. Celsius is kind of related to Kelvin. In some calculations, we'll use Celsius, and in other calculations, we'll use Kelvin. Today, we're going to learn how to convert between them, and I'll talk about, when we get to individual chapters, which temperature we should be using and why we're using that one. But just remember, we're never going to use Fahrenheit in this class. Never, ever, ever. So you'll learn how to convert Fahrenheit into Celsius so that we can use it. Okay? And then, likely you know this already, temperature is always measured using a thermometer. The thermometers that we use in this class will give us our temperatures in Celsius, so we don't need to convert them to Fahrenheit. Just so you know, if we're thinking about room temperature, like 70 degrees Fahrenheit, that's about 22 degrees Celsius or so. Okay, so room temperature is somewhere in the 20s. All right, so like I said, we typically use Fahrenheit to measure temperature. So you will know water freezes at 32 and water boils at 212. And then here's our room temperature is about 72 Fahrenheit. Okay, a nice, comfortable room temperature. So, but temperature doesn't have to just be expressed in Fahrenheit. Like I said, we have two other temperature scales, and actually we won't use Fahrenheit at all in this class unless we're just converting it to Celsius. Okay, Celsius is what we'll use most commonly. The Celsius scale is really cool because it's actually based on water. Okay, so what happens is they took the temperature that water freezes at and they called that 0. And they took the temperature that water boils at and they called that 100. And then they just divided up evenly in between. I think it's pretty logical, right? Just water freezing is 0, water boiling is 100. I need you to know these two temperatures. That's very, very important. So they're pretty easy temperatures to remember, 0 and 100, water freezing and water boiling. So like I said before, room temperature is about 22 degrees Celsius, but you don't need to know that. That's more informational, especially if you're traveling to a different country, right? Assume 22 is going to be pretty comfortable. Things below, you might need a jacket, and things above it, it's like you're living in California in the summertime. So the Celsius scale is directly related to the Kelvin scale. Okay, if you'll notice, to get from Celsius to Kelvin, we're just adding 273. So like here, 100 to 373, right? That's just adding 273. And you'll notice that for all of these temperatures, you're just going to add 273 degrees Celsius to get from Celsius to Kelvin. Okay, so why do we need Kelvin then if it's just adding 273? Well, the cool thing about Kelvin is that there are no negative temperatures. None at all, right? If we talk about temperatures in the United States, oftentimes kind of on the East Coast, right, it'll get really cold and it'll be below freezing, right? And they'll get negative temperatures even. It can get pretty chilly. Well, in the Kelvin scale, you will never have any negative temperatures. So this actually is really useful in some calculations where we need all positive numbers. So especially when we get to gas laws in this class, we'll need to use the Kelvin scale in order to have our calculations work out. So most of the time in chemistry, we'll use either Celsius or Kelvin, depending on what we need for calculations. But I'll be really clear to tell you which ones to use when. So what I do want to point out, though, the lowest possible temperature on the Kelvin scale is really, really useful. Okay, because like I said, there are no negative temperatures. The lowest possible temperature is going to be 0 Kelvin. And this is true just kind of in science. There is no colder temperature than 0 Kelvin. And in fact, scientists actually haven't quite reached 0 Kelvin yet. They're really close. They're at like 0.00000 something, right? So they're really close to 0 Kelvin, but actually they haven't reached it. This is currently a theoretical temperature, right? We think there's no colder temperature than 0 Kelvin, but we don't even know if we can get to 0 Kelvin, which is kind of crazy. So remember earlier when I was talking about the fact that temperature is a measure of thermal energy? Well, if something had, if we were at 0 Kelvin, then that would mean that our substance had 0 energy, which is technically theoretical at the moment, because all particles right now, all particles, even the pencil in your hand, the particles that make up you, the chair that you're sitting on, all particles are moving ever so slightly. They're vibrating in place. And so the theoretical temperature of 0 Kelvin would mean that all motion of all molecules would stop because they would have no energy. So no more vibrating in place for any molecules. So that's why scientists are trying to reach that temperature. They're like, is that really what happens when we get to 0 Kelvin? I think that's kind of cool, right? Science is still in progress. So right now, 0 Kelvin is theoretical, and it would be the temperature at which all motion of all molecules stops. So this temperature has a name. It's called absolute zero. So if you ever hear me talking about absolute zero, I'm talking about 0 Kelvin. Or in Celsius, it would be negative 273 degrees Celsius. So all of the temperature scales, like if we look at these, right, we have a lot of different temperatures for water freezing. It freezes at 0 Celsius, 273 Kelvin, and 32 degrees Fahrenheit. And so like I told you before, sometimes we'll use Celsius for certain things and Kelvin for other things, and we never use Fahrenheit, but if you mistakenly took your temperature in Fahrenheit, you would need to be able to convert it in order to use it in your calculations, right? So we need to know how to get between these temperature scales. So here are some really useful equations. So Kelvin equals degrees Celsius plus 273.15. Okay, remember, we're always going to add 273 to our Celsius temperature to make sure our Kelvin temperature is always positive. If you accidentally do this wrong and you accidentally subtract 273, you should notice pretty quickly because your Kelvin temperature will be negative, or it will be lower than your temperature, or it will be higher, than your temperature in Celsius. Okay, so just keep an eye on that. You'll notice if you ever get a negative Kelvin, you'll know you've done something terribly wrong. And then our temperature for Fahrenheit, if we go Fahrenheit equals 1.8 times degrees Celsius plus 32. Okay, so that will be how we convert between Celsius and Fahrenheit. The top one is between Kelvin and Celsius. And if you ever needed to go Fahrenheit to Kelvin, then just go to Celsius in between. So let's try this. Convert 723 degrees Celsius to temperatures in both Kelvin and Fahrenheit. Okay, so first off, if we were going to convert it to Kelvin, we would take our 723 and we would plug it, right, because this is degrees Celsius, we would plug it in here where it says degrees Celsius. So that's what I've done right here. 723 plus 273.15 gives us 996 Kelvin. In this class, when we're doing these problems, and any problems in general, please make sure to circle your answers or box your answers so I can find them, okay? On quizzes and tests, sometimes it's a little bit hard for me to see what your answer actually is, so make sure, be proud of your answer. Circle it or box it so I can find it easily. All right, and then if we were going to convert Celsius to Fahrenheit, again, we take our 723 and we just plug it in here where it says degrees Celsius. So 1.8 times 723 plus 32, and that will give us our answer in Fahrenheit. Okay, so using these equations, I think, is pretty straightforward. Just plug your temperature in to wherever the unit is, and then solve for the other temperature. I do want you to memorize these equations, okay? The one for Kelvin and Celsius we'll use really frequently throughout the course, and I think it's pretty easy, right? You're going to add or subtract 273. The one for Fahrenheit we'll pretty much just use in this chapter, but I do want you to know how to do this conversion. So please go ahead and memorize that equation as well. All right, I want you to go ahead and try this out. What is the temperature if 98.6 degrees Fahrenheit is converted to Celsius? I put the equations there. You'll need to figure out which equation do you use, how do you plug it in, and how do you rearrange it if you need to. So go ahead, pause here, and then come back when you're ready to see the answer. Alrighty, so we're going to convert between Fahrenheit and Celsius. That means we are going to use this equation here. We're going to take our temperature, this 98.6 degrees Fahrenheit, and we're going to plug that in for Fahrenheit. Okay, so there you go. So we've plugged 98.6 degrees degrees Fahrenheit in right there for Fahrenheit, which is why that's right there. And then we can start to rearrange. So if we subtract 32 from both sides, then that gets rid of that, and we get 98.6 minus 32 gives us 1.8 degrees Celsius. So I've simplified that 98.6 minus 32, that gets us 66.6. Our next step is to divide both sides by 1.8. Okay, we divide both sides by 1.8, we'll get 37 degrees Celsius as our answer. Alrighty, go ahead and pause here and work on problems number 13 to 14 on the Chapter 4 lecture worksheet. This will get you some practice on temperature conversions. Once you're done, come back and we'll move on to talking about density. Alrighty, so we've talked about a lot of different units throughout, Chapter 4, right? We talked about grams and meters and liters and seconds and all of the prefixes that go with them. But there are some quantities that can't be really expressed with those SI base units. So instead, we end up combining some base units together to make appropriate units for what we're looking for. So one of these quantities with combined units is density. Okay, density is a ratio of mass to volume. So that's what we see here. Density is a ratio of mass over volume. Okay, so a better way to write it is density with a lowercase d is equal to mass over volume. You'll notice mass has a lowercase m and volume has a capital V. Remember in chemistry that whether things are lowercase or uppercase matters, so make a note of those. So density is the ratio of the mass of a substance to the volume occupied by that mass. Density is a physical property of the substance. Remember, we've talked about physical properties already. These are properties of substances that can be measured without altering the substance. So we can actually easily measure the density of substances just by taking the mass and taking the volume and dividing them up. We'll actually do this in a lab, so you'll get some practice doing density. The units of density are, like I said earlier, combined units. So we have a couple different ways that we can do it. So we can do grams per milliliter, and that's the most common. This is usually for liquids. We can also use grams per centimeters cubed. That's typically for solids. And then grams per liter is for gases. We won't do much with the density of gases in this class. Mostly we'll be using liquids and solids, so we mostly use grams per milliliter or grams per centimeter cubed. Remember, we talked about previously that milliliters and centimeters cubed are the same thing. So if your density is in grams per milliliter, that's the exact same thing as saying grams per centimeter cubed. So these two units are the same. We just, like I said, usually use grams per centimeter cubed when we're talking about solids and grams per milliliter when we're talking about liquids. But you can use them interchangeably because they mean the same thing. So when we're talking about liquids, the volume of a liquid actually changes at different temperatures. Okay, it doesn't change a ton, but it does change a little bit. At higher temperatures, these liquids actually spread out a bit and end up having a larger volume at higher temperatures, which affects the density because we're changing the volume. So when we're talking about the density of a liquid, we'll always talk about the density of a liquid at a certain temperature so that we know it matches kind of that volume. So if you see that, that's what's happening there. This is an example. The density of water, right, liquid water at 4 degrees Celsius is 1 gram per milliliter, while the density is 0.97 grams per milliliter at 80 degrees Celsius. This is because as the water heats up, it actually spreads out a little bit, which makes the volume bigger and the density smaller. Okay. So here's the density of some common substances. This is just a reference chart, just so you can look and see some common densities. The only one I want you to memorize is the density of water here. Okay, you don't need to memorize that it's at 4 degrees Celsius. I just want you to know the density of water is 1. And that's it. Density of water is 1.00 grams per milliliter because we're going to use that as a conversion factor a bit in this class. So that's a handy one to know. Otherwise, I will always give you these densities. Okay. One thing I want you to know, though, is substances that have a lower density than water will float. So let's say we took a cork, right? We opened, a bottle of wine, and we have this cork. If we put the cork in water, it floats because that water is lower, or that density is lower than the density of water. So the cork floats in the water. Same thing here, right? The density of ice is lower than the density of water, so it floats. However, things that have a higher density than water will sink. So like if we stuck some iron in the water, it'll sink to the bottom, right? Iron's pretty dense. Same thing if you put maybe a gold ring in water, that will also sink. So anything that has a density that's less than water will float, and everything that has a density that's greater than water will sink. Kind of cool, right? All right, thinking about what we were just talking about with the sinking and the floating, which diagram will represent the liquid layers in the cylinder? Okay, so you have three different liquids. You have caro syrup, which is K, vegetable oil, which is V, and water, which is W. And I want to know what's the order that they would show up in a graduated cylinder if I poured them all together. Okay, you'll need to think about the densities for this problem. So go ahead, pause here, think about this, come back when you're ready. Alrighty, so our answer is number 1. So vegetable oil is the least dense, so our vegetable oil will go on the top. The water is the next least dense, right? So it's more dense than vegetable oil, so it will go below vegetable oil, but it will go above caro syrup because caro syrup is the most dense. So we can actually do this whole, it's called a density column, and you can actually order these liquids based on their density, and they'll make these really cool layers. If you're interested, you can check it out. I'm sure there's YouTube and things out there, but it's called a density column. All right, so what is density really, right? We've talked about the fact that density is a ratio of mass to volume, but what does that really mean? Well, essentially what it means is that substances that have a really high density have particles that are closely packed together. So like a brick, right? If we think about a brick and a styrofoam, right? Same size, which one is heavier, right? A brick would be way harder to pick up than a piece of styrofoam. And the reason for this is that all of those particles are closer together than the particles of the styrofoam. So there's more mass in that same volume, right? They have the same volume here, but the brick has more mass, which means it has a greater density. Okay, so the styrofoam, though, has less mass in that same volume, which means it will have a lower density. Density is what we call an intensive property of matter. Okay, and what I mean by that is it doesn't depend on the quantity of matter. It doesn't matter how much of your stuff you have, whether you have a little bit or a lot, the density is always going to be the same. Like I told you earlier, the density of water is 1 gram per milliliter. So it doesn't matter whether you have a little bit of water or a lot of water, the density of water will always be 1 gram per milliliter. So that's what an intensive property is. We did talk about, though, it does depend on the temperature, though, especially for liquids and gases, that density will change based on the temperature. So just so you get an idea of what an extensive property is, that's the opposite of an intensive property. That's where it does depend on the quantity of matter. This would be things like mass and volume, right? If we were to measure mass, well, your mass will change based on how much stuff you have. If you put more stuff over there, then you've got more mass. If you have less of it, then you have less mass. Same thing with volume, right? If you have more of your liquid, then you have a greater volume. So those properties change. Those are called extensive properties of matter, whereas density is an intensive property of matter, and it doesn't matter how much of the substance you have. So I kind of like this depiction. So here are 3 different substances, and you see that they all have the same volume? Okay, if they all have the same volume, then the one with the highest mass has the greatest density. Because remember, density is equal to mass over volume. If all of their volumes are the same, like we show here, then whichever one has the greatest mass will have the greatest density. Okay, we can do a different thing, right? Again, density equals mass over volume. And let's say they all have the same mass. Well, now they're going to have really different volumes for that mass. Kind of interesting. And those volumes are based on the density. All right, let's go ahead and get some practice with this numerically, okay? It's a pretty easy equation, density equals mass over volume. So let's go ahead and try it out. This one says, calculate the density of a substance if 323 grams occupies a volume of 53.0 milliliters. So we have grams and we have milliliters, so we have a mass and we have a volume. Okay, so we can just go ahead and plug that into our equation. Density equals mass over volume. And you can make yourself a note. We want this mass to be in grams and this volume to be in milliliters or centimeters cubed. So since our units already matched, right, we already had grams, we already had milliliters, we could go ahead and just plug them into this equation and calculate the density. You'll notice I rounded my answer to 3 significant figures because each of these had 3 significant figures. And then my units were grams per milliliter to match the units of the problem. We can also use density as a conversion factor in our train tracks. Okay, so this will be really, really useful. You can use density with that density equals mass over volume equation, or you can use it in train tracks. It just kind of depends on the type of problem that you're solving, which way you'll go about it. So this says the density of gold is 19.3 grams per milliliter. What is the volume of 25 grams of gold? So you could do this problem using the density equals mass over volume equation that we were just talking about. But we can also use density as a conversion factor. And this is going to be really useful, like I said, in using it in those train tracks, especially in some more complex problems that we need to solve. And if you go on to higher levels of chemistry, you'll need to use it as a conversion factor in those classes. So I do want us to get used to it. So here we have 19.3 grams per milliliter. So the way that we use this as a conversion factor, do you see it's got 2 units here? So to use it as a conversion factor, we actually are going to split those units apart. This 19.3 grams is going to end up as 19.3 grams, and the milliliter is going to end up on our other side of the equal sign. This number is always going to be a 1, okay? So the number that goes with milliliter is always a 1. And then that 19.3, or whatever the density is, that will always go with grams. Okay, so we're going to split this apart. 19.3 grams equals 1 milliliter. Because that's true. If we had 1 milliliter of this substance, it would weigh 19.3 grams. Okay, so when we are looking at significant figures, though, this 1 milliliter here is not going to play into our significant figures. That's going to be an exact significant figure. So let's look at this. So here's what we're starting with, 25.0 grams of gold. And sometimes people ask me, how do you know to start with the 25 grams and not the density? Okay, well, density is a conversion factor. And we are never, 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 ever going to start our train tracks with a conversion factor. Okay, so just tell yourself, you cannot start your train tracks with a conversion factor. And density is a conversion factor, so no starting train tracks with density. So that's why we're putting our 25.0 grams at the beginning of our train track. Remember, all of our rules of train tracks still apply. If I have grams here, then I have to have grams down here. So that means this portion of our equality is going to go on the bottom. And this portion of our equality is going to go on the top. That's how we make our units cancel there. If you did it the other way around, you would notice that your units don't cancel down and to the right, and they have to in order to be able to use these train tracks. So again, that's why 19.3 grams goes on the bottom and that 1 milliliter goes on the top. Now, we've found milliliters and we were looking for volume. So we found what we're trying to solve for, so we can go ahead and punch this in. So we would do 25 times 1 divided by 19.3, and that will get us our answer. Again, you'll notice I've rounded this to 3 significant figures to match the sig figs in our problem. That 1 milliliter doesn't play into our sig figs because that's exact. All right, I want you to try this, okay? And try it using density as a conversion factor. Try not to use the density equals mass over volume equation just for right now, because I want you to get some practice on this. So try to solve this problem. We want to know the mass of 1.50 milliliters of ethyl alcohol. Okay, so pause here, try this out, and come back when you're ready to see the answer. Alrighty, so our first thing we need to think about is, okay, what are we starting our train track with? Well, remember, we can't start it with density because density is a conversion factor. So we'll go ahead and we will start with our milliliters. Okay, so there's our milliliters. So again, I wanted you to use density as a conversion factor in this problem. So that 0.789 grams per milliliters, we're going to use 0.789 grams, remember the number goes with grams, equals 1 milliliter. And then we need to know which part goes on the top or the bottom. Well, since we have milliliters here, we need to have milliliters cancel down and to the right. So that means that 1 milliliter portion will go on the bottom to make our units cancel. And that 0.789 grams will go on the top. Okay, we make sure our units cancel, and then make sure we found what we're trying to find. We were trying to find mass, and we found mass because grams is mass. So we can go ahead and multiply these numbers out and get our answer. Again, you'll notice I've rounded my answers to 3 significant figures to match the number of sig figs in our problem. So when we're doing measuring density in our lab, a lot of times we will measure the density of weirdly shaped objects. Like sometimes we'll measure things that are regularly shaped, that are cylinders or rectangles or things like that, but most of the time in chemistry, we don't. We have things that are kind of weird shaped. And so instead of measuring them with a ruler, we have a different way of measuring the volume, and that's called displacement. So that's what we're going to talk about right now. But like I said, in order to calculate the density, we need 2 pieces of information. We need to have the mass and the volume. The mass is pretty easy to get, right? If you're going to measure mass, you just take your stuff to the back and stick it on the balance, write down what mass it has. But if you have something that's weirdly shaped, you need to have a plan for how to get the volume. So the way that we do that, like I said, is displacement. And what I mean by that is we're going to take our solid and we're essentially going to stick it underwater, and we're going to see how much the volume of the water changes. That change in the volume of water is going to be equal to the volume of the solid. Okay? So let's take this. If we were to measure the density of this piece of zinc, so we could get the mass by sticking it on the balance just like this. Okay? And the way we would get the volume is we would measure the volume before we add any zinc. So just figure out how much water is in there. And then we would take our zinc and we would stick it in the graduated cylinder. And we would see how much the water level rises. So we would record the new volume. And then if we subtract, right, we take our new volume minus our old volume, that change is going to be because of the zinc, right? That's going to tell us the volume of this zinc. So rather than try and get out our ruler and measure, the diameter and the height, and then we do like the 4/3 pi r cubed h, right? Instead of doing that, we can just measure the volume before, measure the volume after, and subtract them to get the volume of the zinc. Pretty quick and easy, and really useful. So let's try this out in a math problem. What is the density in grams per centimeter cubed of 48 grams of a metal if the metal raises the level of water in a graduated cylinder from 25 to 33 milliliters? All right, so remember, when we're calculating density, we need mass over volume. And this says it wants the density in terms of grams per centimeter cubed. Well, we already have 48 grams. That's our mass. But we need to figure out the volume. Do you see that we have 2 different volumes here, 25 milliliters and 33? That's telling you that we started with 25 milliliters, and then we added our metal, and the water level rose to 33 milliliters. So in order to figure out the volume of the solid, we just subtract them. Really easy. If you're doing density problems, most times that's what you're doing, is you're just going to take your 2 volumes and you're going to subtract them. So that would give us 8 milliliters. But remember, we wanted the density in grams per centimeter cubed. Recall from earlier that milliliters and centimeters cubed are the same thing. So if you know that the volume is 8 milliliters, that means the volume is 8 centimeters cubed. So you can just write that down. You don't need to show me any work for that. That's one of those things that I will just expect you to know. All right, so now we have our mass and we have our volume in centimeters cubed, so we can go ahead and calculate the density. So we'll just plug those in. We've got 48 grams on the top, 8 centimeters cubed on the bottom, and we'll get our density. So we're rounding this to 1 significant figure here because there's 1 sig fig there. Alrighty, that actually wraps up chapter 4. So today we talked about temperature conversions and density conversions. We talked about the density equation and also how to use density as a conversion factor in our train tracks, which will be very handy moving forward. So I do have quite a few problems on the Chapter 4 lecture worksheet for you so that you can solidify mostly these topics of density in your mind before moving forward. Remember, always check your work on the answer key that's posted on Canvas. Do that, kind of as you go to make sure you're doing problems correctly, and don't just wait till the end so that you're not practicing things wrong. If you ever get stuck on these Chapter 4 lecture worksheets or any of the lecture worksheets in these classes, please reach out to me and ask for help. Remember, I teach chemistry because I like talking about chemistry. So you're not bothering me if you have questions. I really do want to answer them and help you be successful in this class. So as always, keep working hard. And if you have any questions, send them my way. Otherwise, I'll talk to you guys next time.